Hi everyone, this lesson is for geometry students. This is chapter 4, day 6. We're going to be talking mostly about the Pythagorean Theorem, but a little bit of geometric means and special right triangles, as well as conditionals. So let's get started. Learning targets presented, and please read over those. We're going to get started with a warm-up as for what does it mean for a radical expression to be simplified. And most people are going to try to see what is the highest perfect square that you can divide into each of your roots. That's what we want to try to do. The square root of 75 can be rewritten as the square root of 25 times the square root of 3, because roots times roots, you can multiply roots, right? For example, if I had the square root of 2 times the square root of 3, I'm going to get the square root of 6. So you keep the root and multiply the numbers inside. So that definitely can be reduced to root 25 times root 3. Square root of 25 is 5. So we got 5 times root 3. Remember, numbers get multiplied with numbers. So this 5 is never going to be multiplied by that root. What it is multiplied by is that 1 in front of that root that we don't see, but we know is there. So 5 times 1 is 5. So we have 5 root 3, and that's my final answer. For this problem here, this breaks down. See, the root goes over the entire fraction. That's going to be the square root of 2 divided by the square root of 5. Now, of course, I can't divide those two fractions, but what I can do is remove this root from the denominator, because you aren't allowed to have that root on the denominator. So we're going to rationalize that. So in doing that, we're going to multiply it by itself, because whenever you have a root on the denominator, whatever the value is, if you multiply that value, if it's a square root, by itself, it's going to go away, meaning, watch what happens. And by the way, I can multiply by 1. See, root 5 divided by root 5 is 1. And I can multiply anything by 1 and still get, you're not changing the problem, so that's completely fine. So we have root 2 times root 5, that makes root 10. And root 5 times root 5 is the square root of 25, right? But the square root of 25 is 5, because 5 times itself. Okay, so we have root 10 over 5. And we're done, because you can't break into roots and numbers. Quick segue into square roots. And I just want to mention this because not a lot of people actually know why the root. I just kind of glossed over that the square root of 25 is 5. But a lot of people might want to know why, right? So basically just rewriting that is the square root of 25, right? And that's going to be actually, square root of 25 is 5 times 5. So we can rewrite that as 5 squared. A square root, like that actual root, is a half power. So like if it was, there's a 2 there, but you don't see it. And if it was just like x to the square root of x, there's a 1 there, but you really don't see that also, right? So if you wanted to rewrite the square root of x, you could rewrite that as x to the 1/2 power. Now, that being said, if I have a 5 underneath the 1/2 power, right? I've got that root becomes a half power. I have 5 squared, and then this is to the 1/2 power. Those 2's are going to cancel, and you just get, 5. So that's why the root goes away, because it is a half power, and it's like you're squaring a value. So again, if I had the square root of 36, right? Most people know the square root of 36 is 6. Few people know why that is the case. And the reason why is, again, square root of 36 is just 6 squared. A root is actually a half power, right? And so therefore you've got 6 squared, and then it's to the up power, 1/2 power. Those 2's are going to cancel, and so you just have 6. That's why, right? Learn something every day. 2 square root of 48. I'm thinking perfect squares. So there's definitely a couple of options here. You could go 2 times square root of 16 times the square root of 3. That's my initial thought. Square root of 16 is 4. So we've got 4 times 2 times the square root of 3, which makes 8 root 3. And so that would be the answer to 2 root 48. Now, that being said, of course, a lot of kids think, well, that's 8 times 6, square root of 8 times square root of 6. Well, square root of 8, you can actually break that down even further, right? To the square root of 4 times the square root of 2. And the square root of 6 is the square root of 3 times the square root of 2. and I'm running out of room. So I'm going to move some stuff a little bit so I can get that out of our way here. Whoops. Okay. All right. Anyway, so what we do now is the square root of 4, right, is 2. So that's a 2. 2 times 2 is 4. So we have 4 times root 2. We have times this stuff, which is root 3, times another root 2. Root 2 times root 2 is root 4. Those are going to go away. Square root of 4 is 2. So we have 8 root 3. I mean, definitely some options for solving 2 root 48. But, use which one you feel most comfortable with. Square root of 64 is 8. Square root of 4 is 2. 8 times 2 is 16. Yes, you could have multiplied root 64 times root 4 and gotten root 256, right? Which is going to be 16. But, if these are perfect squares ahead of time, then simplify that, of course. Another root on my denominator, you must get rid of that. So we're going to multiply by that same root over itself. So basically I'm multiplying by 1, which means I'm not changing the problem. So on the top, on the numerator, I have 15 root 5 over square root of 5 times square root of 5, square root of 25, right? Square root of 25 is 5, which is the whole point in multiplying by itself so that the root goes away. So now I have 5 because numbers can divide into numbers. So I have 5 divides into 15. I'm going to erase this because I am running out of room here. And so we have 3 and then root 5. So 3 root 5 is my answer. 3 root 5. Okay? Now, we're going to start off talking about conditional statements. So a conditional statement has a hypothesis and a conclusion. It's like, if this happens, then this happens. It's got a consequence. Like you used to have that with your kids, right? If you don't clean your room, then you don't get to go outside. Consequences. If you don't learn how to swim, then you can't go in the pool. If you don't vacuum, then you don't go to the movies. Whatever you guys said. A statement could be true. An actual true conditional statement can be tested. So if it rains, then PE will be inside. So what happens if it rains? PE will go inside. Well, what happens if it doesn't rain? Can PE still go inside? Yeah. What if you said PE went inside, therefore it rained? So you've got, you can flip this around and try to make sense of it, but usually it's something that can be tested. So for these conditional statements, it says identify the hypothesis. That's the beginning statements. It does not include if. And a conclusion when each statement is written in if-then form. So we don't have the if-then form, we just have the statement. So congruent lines have the same measure. So for this statement, you would say, I would say, if line segments are congruent, then they have the same measure. Okay, so my hypothesis does not include the word if. So you'd say, what's the hypothesis? Line segments are congruent. And then what's the conclusion? Doesn't include the word then. They have the same measure. So that's what that is. Now, here's another one. A triangle has 3 sides. So if I wanted to put that in an if-then statement, I would say something like, if a shape has 3 sides, then it is a triangle. And so that's one option. So the hypothesis might be a shape has 3 sides. Conclusion doesn't include the word then. It is a triangle. There are at least 3 points in a plane. So putting that as a conditional, you would say if there exists 3 points in space, then a plane may be determined. Or if the shape is a plane, then it must have at least 3 points. Because 2 points make a line, right? But 3 points actually make a plane. If today is, okay, so now those are the conditionals. That's like if then. So then they want to know to write the converse. Now the converse takes your hypothesis and your conclusion and does this, flips it. So my conclusion is now my hypothesis. My hypothesis, or my conclusion, is now my hypothesis. So these are statements that say if it is July 4th, then today is a national holiday. So that's a true conditional. Yes, July 4th, if it's today, July 4th is a national holiday, right? However, if I write the converse, which says if today is a national holiday, then today is July 4th. Well, I did write the converse, but is that a true conditional? If it's a national holiday, it could be Veterans Day. It doesn't have to be July the 4th. So there's a lot of different, things that could come up. We call those things that come up to prove a statement wrong counter examples. So, okay. All right. So the converse of this one, so it says all right angles are congruent. So if a triangle is right, then the right, we're not saying an if then. We're just saying all right angles are congruent. So flip that around. I could say if it is a right angle, then it is congruent. So if the angle is right, then it is congruent. Well, doesn't have to be necessarily. So it's like some of these, when you flip them, don't have to be actually true. If x plus 5 equals 8, then x equals 3. Well, if I flip that around and I say, well, if x equals 3, then x plus 5 equals 8. Okay, that does work when I flip it around. So some of these, again, just the point of the converse is to take your statement and your hypothesis and conclusion, and it flips. Now, the geometric mean is actually defined as a value that is in between two others geometrically. So basically, we know what an arithmetic mean is, right? It's where you add up, the mean is the average. So an arithmetic mean is where you add up all the numbers and you divide by how many numbers you have. That is not a geometric mean. A geometric mean is different. So if a geometric mean is if A is to X as X is to B, then X is the geometric mean. So between A and B. So the way you would write that is this. You'd say cross multiply because you have one term on the left and one term on the right. So basically you could say X squared is equal to A times B. Okay. So what is the geometric mean between 4 and 9? You will need to do this. This also is on your SAT. So make sure you do know this. The geometric means you would say 4 is to X as X is to 9. You're going to cross multiply X times X, which is going to give you X squared equals 4 times 9. Well, 4 times 9 is 36. So X squared equals 36. And therefore, X is equal to 6. Now, in geometry, most of the time, now we know that the square root of 36 could be positive or negative 6. However, in geometry, when we're using lengths and measures and that kind of thing, we know that the negative part of the positive or negative 6 is not, we're not taking that into account because the geometric mean is always going to be positive. So, when you're measuring a length, you're going to say, nope, that's not negative so many inches. You're not going to do that. So find the geometric mean between 3 and 9. You're going to go 3 is to X as X is to 9. Cross multiply, we get X squared is equal to 3 times 9, which is 27. So 27 equals X squared. I'm going to take the square root of both sides to get rid of this 2. And therefore, we get X is equal to, try to think perfect squares, and the square root of 9 is a perfect square, times the square root of 3. Well, the square root of 9 is 3, and 3 times root 3 is 3 root 3. And so that's what my value of X is. So that's my geometric mean. Find the geometric mean between these two values. So you've got 5a cubed bc squared over x is equal to x over 4abc. And so we're going to go x squared is equal to this times that. So we're going to say 5a cubed bc squared times 4abc. Now a geometric mean, again, or a square root, a square, when I square root both sides, it's going to cut all my values in half, right? Because remember, a root is a half power. So first I'm going to simplify. So what I have is x squared equals 5 times 4, which is 20. I've got a cubed plus a, that's a to the 4th. B times b is b squared. And c squared times c. Remember the rule, you guys. When you're multiplying the same variables, you keep the base and add the exponents. So that's just going to be c to the 2 plus 1, which is 3. So when I square root both the sides, right, square root of 20, I'm going to go back to 4 times 5. Go figure. And then we've got a to the 4th, b squared, and then c squared times c. See how I broke that up? Reason is because I'm looking for half powers. I'm trying to find, you know, what's going to make the most sense to find a half. And so for this value, square root of x squared is just x. Square root of 4 is 2. That came out. Square, and this stays. A to the 4th, that's half of that power is a squared. B squared, half of that is b. C squared, half of that is c. So these all came out. Those are all, we're all happy that's gone. It looks like we still have a c to the 1 power and a 5 to the 1. So then that's going to be times 5c. And so this right here would be the geometric mean for, or between those two numbers. The next one says, find the geometric mean between 64 and 49. So you're going to say 64 is to x as x is to 49. We're going to cross multiply. We're going to get x times x, which is x squared, is equal to 49 times 64. Well, I'm not going to actually multiply those together because when I square root both sides, I can split these up. Now, keep in mind, you absolutely cannot split this up. This is not what I'm talking about. You cannot do this. 49 plus that. That does not, absolutely not. Okay? Absolutely not. But what you can do is you can multiply. And so what we have is x is equal to the square root of 49 times the square root of 64. Well, square root of 64 is 8. Square root of 49 is 7. 7 times 9 is 56. So my geometric mean for between 64 and 49 is 56. Now, where did the geometric mean come from? Well, it has to do with an altitude. Here's a theorem, right? Theorems we can prove. So if the altitude is drawn to the hypotenuse, so we have a right triangle. So what they did was they started off with a right triangle like this, and then they took the altitude, which is that height, and they drew it to the hypotenuse. This is my hypotenuse. So they drew an altitude straight down. And altitudes are always, by the way, perpendicular. So what you have now is 3 right triangles. You've got the one on the right, you've got the one on the left, and then you've got the large one. So you're basically talking about similar triangles. And so the way you would write like one of these, like if I wanted to find this altitude, I would go this side x is to the height as the height is to y. That's my geometric mean. So I could go x is to h as h is to y. Completely fine. Okay. And I could also do like hypotenuse is to a leg as the hypotenuse, that's my hypotenuse for that little triangle, is to like another leg. So, you know, you can do a bunch, we're going to definitely revisit this, but there's a lot of proportions that you can make for the geometric means. Okay, so moving forward, we're just going to be discussing the Pythagorean theorem. Well, this guy, old guy, right, he's dead now, his name's Pythagoras, and he came up with this way to, this like super cool thing where he's got a right triangle. And what he came up with was this. What he discovered was this. He discovered that the square, okay, of the hypotenuse. Now remember, you see this little right triangle in here, okay? He discovered that the square of this hypotenuse, which is this length right here, which he calls C, the square of that hypotenuse is equal to the sum of the squares of both of these other sides, which means that this is A and this is B, meaning C squared, which is the area, this right here, right? That whole thing equals this area plus this area. That's what he came up with. So his formula works like this, and it says A squared plus B squared is equal to C squared. Please don't get confused, and you note that you can always flip the sums around. So I could have said b squared plus a squared is equal to c squared. And I can even use different letters, like in this problem down here. It looks like my hypotenuse is z. So it's always going to be a leg squared plus a leg squared. So my legs are not the hypotenuse, right? This is a leg. This is a leg. The hypotenuse is opposite the right angle, always. And so, yes, the letters are going to change, but that nothing else is with that. So this is z, right? So that's my hypotenuse. So I can say x squared plus y squared is equal to z squared. Okay, so we do have in some of these problems, which we're going to be doing, is some familiar sides that actually will come up over and over and over again, meaning they just work every single time. And so it's kind of cool that, you know, you can memorize these. And so when you see these come up again, you don't actually have to solve them because you got it committed to memory. For example, we have a 3, a 4, and a 5. By the way, the hypotenuse always has the longest side, okay? Always. It's always the longest, okay? Always, the hypotenuse. So you would say 3 squared plus 4 squared equals 25 squared. We've got 9 plus 16 does equal 25. Sorry, not 25 squared. Whoops. 5 squared. And so, that letter equals 5 squared, which is 25. So, this is 1. This is 25 equals 25. And all of these, we call them the Pythagorean triples, okay? So basically, these are like our familiars. We know that all of these, we've got a 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25. But the thing with this is that there's also multiples. So like a lot of you have probably seen this one, 6, 8, 10, right? Well, if you've seen 6, 8, 10, that's a multiple of the first one, which is 3, 4, 5, right? If I were to multiply by 2, I'd get a 6, 8, 10. If I multiplied by a 3, right, I'd have a 9, 12, 15. Not to be confused with this one, right? Different one. And so basically they're multiples of each one of these. So you can come up with your own multiples, right? And I see a pattern, but it doesn't work all the time, so then it's not a thing. But I wanted to share that with you. If I square 3, I get 9, and I square 4, I get 16, I square 5 is 25. What I'm looking at is the numbers, right? 5 plus 4, these two right numbers is 9, square root of 9 is 3. 12 plus 3 is what? 25, square root of 25 is 5. 24 plus 25 is 49, square root of 49 is 7. But the thing is that it doesn't work for the middle one, so it's not a thing. But I kind of thought that was cool. Okay, so your job is to solve these two triangles and using the Pythagorean theorem. So I would say pause your screen and try to do that yourself, and then restart the video as soon as you're done. So hopefully you were able to spend some time doing this first problem. So what you need to remember is that isolate the hypotenuse. So we know 12 is the hypotenuse because it's opposite the right angle. So however you set up your equation, you always know that the hypotenuse has to be on its own side, right? So we've got a squared plus b squared equals c squared. We've got leg squared plus leg squared equals hypotenuse squared. So my first leg is x. We're going to square that. My second leg is 4. We're going to square that. So we have x squared plus 16 equals 144. And I'm going to subtract, right? I'm going to go 144 minus 16, and I get 128. So I get x squared is equal to 128. Now I'm going to square root both sides because I am trying to find x. I'm trying to find the value of that side. And so I get x is equal to, and now I've got to try to figure out what's the highest value that would go into 128. That would still give me a perfect square. I'm thinking 8, but let me check. We're going to go 128 divided by 8. Is that going to, that's 16. Yeah. So what I have here is not the highest one, but I do know that 128 can be broken down to the square root of 16 times the square root of 8, right? And now that I'm writing, I just wrote that down. I know it's 64, but anyway, square root of 16 is 4. times the square root of 8, but the square root of 8 also can be broken down, right? That can be broken down to root 4 times root 2. So now I've got another root. What's the square root of 4? 2. So that's going to go out front, and you multiply those numbers out front, okay? So now you have x is equal to 2 times 4, which is 8. Leftovers are root 2. And so that's the value of x. And this is 8 root 2. And you are not going to change those roots. Those roots are what we call exact values. I do not want a decimal approximation for that, period. Do not make that into a decimal. Exact values are exactly what I need, okay? So for this one right here, I already recognize this as 10. I hope that you start recognizing some of these too as your triplets, right? You've got 6, 8, 10. But if you forgot to recognize that that's a 6, 8, 10 triangle, then you absolutely can use the Pythagorean theorem. You're going to go leg squared plus leg squared is equal to the hypotenuse squared. 6 squared is 36, 8 squared is 64, is equal to z squared. So you have z squared is equal to 100. You're going to square root both sides, and you get z is equal to 10. And that's what z is. Now, keep in mind, this is work shown. I do expect to see work shown if you are expecting to get credit, right? Okay, so we have a couple of, what's wrong with this? We know that leg squared plus leg squared. So it should be 5 squared plus x squared. Right off the bat, that's what's wrong. It's always leg squared plus leg squared, okay? So now we have 4 squared plus x squared. So we have, I'm going to just rewrite it myself. X squared plus 4 squared is equal to 2 root 5. By the way, that should be quantity squared. See that 2 right there? They only put the 2 on the root 5. But it's a quantity squared, okay? So we've got x squared plus 4 squared, which is 16, is equal to 2 root 5 times 2 root 5. Remember, numbers get multiplied with numbers. So that 2 is going to get multiplied by that 2, and that makes 4. Root 5 is going to get multiplied by root 5 and make root 25. And so that's that times 25, sorry, and that's what? Root 25, 5. And so I have 5 times 4, which is 20. So I've got x squared plus 16. So I'm going to subtract 16, and I get x squared is equal to 4. I'm going to take the square root of both sides, and the square root of 4 is 2. And, I know a lot of people know square roots and all of that, and that's great. If you ever get stuck where you're kind of like, I just don't know what to do with that, you can always break it down 4 as like a factor tree, right? 2 times 2, and just rewrite that as 2 squared. Because 2 squared, when I take the square root of that, right, square root of that root right there is a half power. So it's really saying 2 squared to the 1/2 power. And then those 2's are going to cancel and make 1, so my answer is 2. Obviously, lots of ways to do this, just one way. The length of one side of a square is 6 inches. There we go. What is the length of the diagonal? So we've got, this is what I want to know what that is. So if this is a square, right, squares have 4 congruent sides, which means that's 6, that's 6. So that means when I use Pythagorean theorem, I'm going to get 6 squared plus 6 squared is equal to x squared. So I've got 36 plus 36, which is 72, is equal to x squared. Now I'm going to square root both sides, and when I do that, I'm going to square root both sides. I get x is equal to the square root of 72. Well, I know that that's the same thing as saying 36 times 2, or root 36 times root 2, like that. And so what I'm going to get is x equals 6 root 2. So this value right here for x is actually 6 root 2. Now, I want to make sure that, I want you to be aware of something. This is a right triangle. This right triangle is a square, which means that if these are congruent sides, that means it's isosceles, right? And if it's isosceles right triangle, that means that these base angles are exactly the same value, meaning they're 45s. When this brings me to my first special right triangle, okay? Which means that if it's a 45, 45, 90, like this, 45, 45, 90. If it's a 45, 45, 90, we call it special right triangle. That means that whatever value this is here, whatever, it's the same right here. So that was x, that's x. This value right here will be x root 2. If this is 5, this is 5. This value will be 5 root 2. If that's 10, that's 10. This value is 10 root 2, like that. Okay? So that right there is, special right triangles. Now, there is a little trick in that, because going backwards can always be an issue, right? Meaning if I know that this is, let's say 12 root 2, well, x root 2. So that means x must be 12, right? And then if I said, well, let me change this number right here and say, well, that's 5 root 2. Well, then this would be 5 root 2. Well, the problem comes in because I know that this side needs to be x root 2, right? But what would happen if I didn't make it a root 2? What would happen if I said this side was 10, find x? Well, I actually have some options. Option A, I know this is a isosceles right triangle. I can go x squared plus x squared is equal to 10 squared. 2x squared, because I have two x's, 2x squared. So we go 2x squared equals 100, divide by 2. I get x squared equals 50. And now I'm going to square root both sides, and then I get root 25 times 2, which is 5 root 2. So that means that one of these sides is 5 root 2. Now the rule, okay, is that you take the 10 and you cut it in half and multiply by root 2. That's like the little trick. But realistically, you can always set this to x root 2. Like 10 equals x root 2. Divide by root 2, you get x equals 10 divided by root 2. And go, wait, I need to multiply by root 2 over root 2. So now I have 10 root 2 over 2, or 5 root 2. So there's definitely a lot of options in order to find that side. But if you can just remember, right, to cut that in half, so meaning, again, if I have a root and I say this side here is 12, and the rule is basically take that value, divide by 2, multiply by root 2. So the side should be 6 root 2. That's the little rule. Now you can, of course, go, well, I know that equals x root 2. X root 2. Well, if 12 is equal to x root 2, then x is equal to 12 divided by root 2. I could multiply by root 2 over root 2, and I get 12 root 2 over 2, which becomes 6 root 2. Same thing. But, however way you do that, what this is called is a 45, 45, 90 special right triangle. Meaning, they didn't give me two sides, because to use the Pythagorean theorem, I need two sides, but they only gave me one. Most of the time, they'll give you two. So this is the converse of the Pythagorean theorem. And with the converse, not the Pythagorean theorem, because if you're using the Pythagorean theorem, then it's a right triangle, right? If a squared plus b squared equals c squared, it's a right triangle, period. What you need to distinguish and you need to understand is that not all triangles are right, first of all, and some of them are acute and some of them are obtuse, but we can use the converse of the right triangle, which is, the converse of the Pythagorean theorem, in order to figure out which triangles are obtuse and which are acute. So if you look at this little c squared greater than a squared plus b squared, meaning my hypotenuse, if I square the sides and my hypotenuse is greater, then it's obtuse. But if I square the sides and my hypotenuse is less than the sum of the other two sides, then it's an acute triangle. So we're going to practice. Right here we have 7 squared. So we're going to go two smaller sides, right? We're going to go 7 squared plus 8 squared is what? 10 squared. So we've got 49 plus 64 is what? to 100. So 49 and 64, right? 49, 3, 6, 7, 8, 9, 10, 11 is 113. So the sum of the sides, so my hypotenuse is less than the sum of the sides. So if my hypotenuse is less than the sum of the sides, then then this triangle right here is actually an acute triangle. If I square the smaller sides, right, these two, and we go 8 squared plus 15 squared is what? To 17 squared. What's that? 289, 225, and 64. That looks like they're equal, 289 and 289. That means if they're equal, this must be a right triangle. And oh yeah, look, 8, 15, 17 is one of our little triplets, right? So that works. In this one, we have 3, 7, and 9. We're going to go 3 squared plus 7 squared is, I'm not sure, to 9 squared. So we've got 9 plus 49, and then we've got, that's 81. So obviously 81, my hypotenuse squared, my c squared is larger, which would make this an obtuse triangle, okay? And I think that's what this stuff is. Yep, just saying what they are. So then we're back to 45, 45, 90 right triangles. And remember, on the previous page, when I was talking about Pythagorean theorem, and I was talking about a right triangle that was isosceles, meaning we had two sides that were congruent, I gave you a little formula that said x, x, x root 2. Okay? Whatever this side is, that's the same side because it's isosceles. And then the hypotenuse is x root 2. And so what you're looking at is if these are the same values, you've got x, x, x root 2. So in this case, 3, 3, this answer is 3 root 2. And so when you're doing this, right, you absolutely, if you're given two sides of a triangle, yes, you can use the Pythagorean theorem, meaning I could go 3 squared plus 3 squared is my hypotenuse squared. 9 plus 9 is equal to my hypotenuse squared. We've got 18 equals the hypotenuse squared. Take the square root of both sides. Hypotenuse equals the square root of 18. Well, the square root of 18 is actually the square root of 9 times the square root of 2. 3 root 2. Well, yeah, I absolutely can do the Pythagorean theorem and figure this out. But if I know that this is a 45, 45, 90, I can also just use my brain. Like 5, 5, this must be 5 root 2. 6, 6, 6 root 2. Do you see what I'm saying? You can use any number that works. Now, the problem comes in when there's two issues. One issue is when I don't know this value here. But what I do know is that whatever that value is, it's the same as this value over here. So for this one, I can go x squared, because I don't know this and I don't know this. But I know that because this is a 45, 45, 90, I know that they're the same. So I can go x squared plus x squared equals 6 squared, which is 36. 2x squared equals 36. X squared equals half of 36, which is 18. So therefore, what do I know? I know that if I square root those sides, I just did this on the other problem. X is equal to 3 root 2. So what that means is that this value for x is actually 3 root 2. So again, and I remember telling you on the previous slide what the rule was. If you had the hypotenuse, you take 6, divide it by 2, and multiply it by root 2. And you get 3 root 2. So the side lengths are 3 root 2. So let's do that one more time. If I have a right triangle and I say, let's say that's 10, right? And I know it's isosceles. I either have two sides are congruent or I've got a 45-degree angle. I'm going to take that 10, I'm going to cut it in half, and I get 5. And then I'm going to multiply that by root 2. So I get 5 root 2. Okay? All right. This is x, these are both 45. My job is to find the hypotenuse. And so in order to find that missing side, I'm going to go x, x, x root 2, x root 2. So this is x, this is x. So if this is 4 root 2, this is 4 root 2. And this then is x root 2. So 4 root 2, root 2. Well, 4 root 2 times root 2 is actually 4 root 4, but root 4 is 2, so 4 times 2 is 8. Done. Okay, so the ratios for this is just basically x, and then x root 2. And that works for a 45, 45, 90, and that's my special right triangle. I also have another special right triangle, and this is what we call a 30, 60, 90. I like to use a different letter just because I try to keep the distinction between the two. With the 45, 45, you have two of the same angles. You always use root 2. However, with the 30, 60, 90 right triangle, you're going to use root 3. Let me show you. Across from the 30-degree angle is A. Across from the 90, not 60, across from the 90-degree angle is 2A, okay? People think, well, it's 30 and 30 is 60, therefore it's 2A. That's not true. Across from the 90 is 2A. And across from the 60-degree angle is what we call A root 3. And what that means is I can have a right triangle, any right triangle, and if this is a 30, 60, 90, whatever this value, let's call it 5. So then opposite the right angle is 2 times that, that's 10. Opposite the 60 would be A, which is 5, root 3. Okay, do it again. You've got a 30, 60, 90 right triangle. Opposite the 90, I'm going to say is 12. So that means that this value here is equal to 2A, which means that A is 6, which means across from the 30 is 6. So therefore, across from the 60 degree is going to be 6, right? A root 3, 6 root 3. So these are, like, we call these our special right triangles because we don't have to use Pythagorean theorem. We can just use our brain, right? And so how's that working for you so far, right? So what we have here is a 45, 45, 90 right triangle. I can go x root 2. I can say, I know that's supposed to be x root 2, right? And I know I can divide root 2, and I have 8 over square root of 2. I'm going to get rid of that root 2. I'm going to multiply by root 2 over root 2. I'm going to get 8 root 2 over root 4, which is 2. Those are going to cancel, and I get 4 root 2. Oh, my sides are 4 root 2. Or you can go, oh wait, I know the little shortcut. I'm going to take 8, I'm going to divide by 2 and multiply by root 2. And so I get 4 root 2. So I could do that also. For this problem, remember, this is a special right triangle, but it's a 30, 60, 90. Across from the 60 is root 3, A root 3. So that means A is 7. So across from the 30 is A, which is 7. Across from the 90 is 2A. So if A is 7, because that's opposite the 30, then 2A is going to be 14. Here's just special right triangles again. X root 2. So 2 root 2, 2 root 2. This side here, x. So x is going to equal, 2 root 2, root 2. Because remember, this side here, right, is if this is x, then this side is x root 2. So we're going to go x root 2. So if this is x, that x goes right there. So you've got 2 root 2 times root 2. 2 times root 2 times root 2 is root 4. Square root of 4 is 2. 2 times 2, 4 is equal to x. This one is not a right, yes, it's a right triangle. But because the sides are different, it's not isosceles like a square would be isosceles, right? So it's not, I can't use any tricks. I can't use special right triangles. I can use the Pythagorean theorem. Or I can remember that this is a triplet, right? Remember the triplets? What are the triplets? You got to remember these. There's 3, 4, 5, 5, 12, 13, 8, 15, 17, and 7, 24, 25. So this one is this one, 8, 15, 17. Z is 17. You could have used the Pythagorean theorem and gone 8 squared plus 15 squared equals 17 squared, right? And then that would have been that. You can do that too. I see that these two angles here in this right triangle are congruent, which then makes my sides congruent. So 12, 12, 12 root 2. And these make 45-degree angles. If I have one 45, I've got two 45s, which means they're congruent again. This is x, x, x root 2. Rule, take half of 8, which is 4, and multiply by root 2. So these sides are 4 root 2. Find the height of the trapezoid. So what we know is the height, which we'll call it h. This is an isosceles trapezoid, right? So that means it's symmetric, meaning like that side has to be the same as that side too, right? So if I know that this distance from here to here is 10, and the whole distance is 22, 22 minus 10 is 12, right? And if this is isosceles, that means that this side and this side are the same value, so that must be 6. This is a right triangle. I don't know anything about my angles, but I do know that it is a right triangle. I do recognize that it's a Pythagorean triplet, which means that my height is 8 because it looks like a 6, 8, 10, right? However, I would just, I could do this for you and just go, well, that's 6 squared plus h squared is equal to 10 squared. So h squared is equal to 100 minus 36. So h squared equals 64. So h is equal to 8. And that's where that height came in as 8. For this problem on the right, this is, I don't have enough information. What's my height? I don't know anything about this triangle. Let me put some information in, and let's just go ahead and say this is isosceles. Otherwise, I don't have enough information. Let's see. What else would I need to know? If that's isosceles, then these angles are equal, but they don't give me an actual value. So I'm going to have to even go a little bit further and say I need a side or something in order to find this. So I'm going to actually say that this is a 30, 60, 90 right triangle. That's what I'm going to do. 30, 60, 90, since we're talking about special right triangles, right? So across from the 30 we know is a, across from the 90 is 2a, and across from the 60 is a root 3. So if I know this length here, which is a, if this whole thing is 4, and knowing that this, of course, does have to be an isosceles triangle to be able to split this up into 2 equal parts, that would have to be 2. So across from the 30 is 2. Across from the 90 would be 2 times 2, which is 4. And then across from the 60 would have to be a root 3. If a is 2, then y would have to be 2 root 3. Here we go. Find all this side. So here I actually have an angle, but I'm missing the right angle, but that's okay. 60, here's a 30. So across from the 60, now this is the trick one. Across from the 30 is a. Across from the 90 is 2a. But across from the 60 is a root 3. So what they're saying is that this value is equal to a root 3. So we're going to go a root 3 equals 3. We're kind of going backwards because I don't have two sides. I only have one side. So I actually can't use the Pythagorean theorem unless I know how to use this special right triangle. So I do need to solve for a. I'm trying to find out what's across over here. So I got to divide by this root 3. So I have a equals 3 divided by root 3. So now that's gone. Except for, of course, there's always something. I can't leave a root on the denominator. So I need to multiply by 1, but in the form of root 3 over root 3. So I get 3 root 3 over root 3 times root 3 is the square root of 9. Square root of 9, 3. These are going to cancel. So a is actually equal to root 3, which means across from the 90 is 2 root 3, because that's 2 times that. Okay, rhombus. Okay, what you should remember about a rhombus is that the diagonals make little right angles. You also should remember that all the sides are congruent in a rhombus. So 4 congruent sides, diagonals make perpendicular lines. That makes that a 30, 60, 90. It means that across from the 90 is 6, and that's 2a. So this value is equal to 2a, which means that a is going to be 3. which means across from the 30 is 3, which means it's a diagonal split in half because they're bisected, so that's 3. What else do we need to know? We know that that's 3. Opposite the 60 is a root 3, so that's going to be 3 root 3, and then 3 root 3, which makes 6 root 3 for one of my diagonals, and then my other diagonal is going to be 3 plus 3, which is 6. I've got all the sides, that's it. Okay, for this one, to find all the sides and angles, I know that's 30, so that must be 60 and 90. Because these are congruent and it's a right angle, that also means that the angles are the same, which would only mean that they're both 45 degrees. So this is a little tricky for sure. But looking at the top part, I know across from the 90 degree, right, is equal to 2a. So 2a equals 12, right? So 12 equals 2a, so a equals 6, which means that across from the 30 degree angle is 6. Then across from the 60 degree angle is a root 3, so that's going to be 6 root 3. Now, likewise, I know this triangle, the 12, also, if it's a right triangle and the special right triangle with 45, 45, 90, that this would be x, remember, that equals x root 2. So if I have 12 is equal to x root 2, x is equal to 12 divided by root 2. Again, don't leave a root on the denominator. You're going to multiply by root 2 over root 2. So I have 12 root 2 over 2, which makes 6 root 2. So both of my sides then are 6 root 2. And I'm done. So that's a really great introduction to Pythagorean theorem, geometric mean, some conditionals, and special right triangles. So thank you so much for watching, and I hope that helped you. Homework is 2.3.2. Good luck.